Hello and welcome to the latest in the Student Revision Tutorials, Unit 3 Specialist Mathematics with TI-Nspire. My name's Peter Flynn and this morning we will have a look at vectors. An overview of the webinar. It's quite a busy webinar. We'll start off by reviewing vector representation and algebra in the plane. We'll look at unit vectors. We'll look at the scalar or dot product and its applications, for example, finding an angle between two vectors. And then we'll look at the idea of a cross product and equations of lines and planes. Now, I'm just going to move to the TI-Nspire file. I'm going to reference, on occasion, Cambridge Specialist Maths Units 3 and 4. And there are some pages in this TI-Nspire file that were made by a very clever person called Stephen Crouch, and I would like to acknowledge his expertise in constructing these pages. So without further ado, let's have a look at a review of vector addition and subtraction. What we see on the screen there is a vector A and a vector B. Notice geometrically that a vector has a tail and it has a head. And so what we want to do is we want to form the vector A plus B, and it is understood geometrically to follow the head to tail rule, or indeed the triangle rule. So if we click there, what we see is vector A plus vector B gives vector A plus B. So the tail to the head there. When we look at subtraction, here we want to form the vector A minus C. So we have two vectors here. We have a vector A and a vector C. Notice that vector C is in that direction. If we click on this, we see that vector minus C is in the opposite direction, still the same magnitude, and then by the head to tail rule or the triangle rule of vector addition slash subtraction, here is the resultant vector A minus C. So vector A plus vector minus C. And what you can do is you can grab and move vector A around the plane. You can move vector negative C around the plane, and you can see that it still forms that triangle. Next, we'll have a look at multiplying a vector by a scalar. A scalar is a real number. So here we have vector A. To form vector 2A, which is a vector in the same direction, it's got a magnitude twice the size of vector A. All we do is it's basically vector A plus vector A gives vector 2A. Here is the corresponding vector 3A. You might also consider that if you wanted to go in the opposite direction, here is our vector A, and there is our vector negative A. It's the same magnitude, it's in the opposite direction. The angle that those two vectors make between their two tails is 180 degrees, or pi radians. So looking at features of the Nspire, the magnitude of a vector and unit vectors. Now the magnitude or the size of a vector can be found by using the norm command. Now in numbers, now be careful because the numbers may change, although that's quite unlikely. The norm command, what you do is you, actually I'll show you in a minute, you would press menu, then matrix and vector, and then norms and then norm. And the unit vector, which is like a direction giver, it's a vector with a magnitude of 1. And the unit vector A hat of the vector A, that can be found by using the unit vector command. So you go to matrix and vectors, and then C for advanced vector operations, and then number 1 is unit vector. And I'll show you that just in a moment. So our first example is quite a straightforward one. Find a unit vector in the same direction as u equals 2v minus w if v is that vector and w is that vector. So they're vectors in 3 dimensions. I, j and k are unit vectors. They're mutually perpendicular. And what we want to do is we want to find a vector of magnitude 1 that's in the same direction as that linear combination of v and w known as u. U is 2v minus w. And what we're going to do is we're going to assign V and W to be these vectors. They're going to look a little bit different to normal vector notation, but it works quite nicely. So in questions where you have quite a few parts to the question and you're dealing with a couple of vectors in, say, 5 or 6 parts, it's a very good idea to assign the vectors. And so I'll show you how that works now. So the first thing we're going to do is we're going to take vector V and we're going to press Control Symbols Template. That's the assign command, colon equals. Then we want a square bracket. And then what we want to do is we want to enter the components and we separate them with a comma. So we have 2, comma, -3, comma 5, and then press enter. And so we now have vector V has been assigned. Now notice that I'm using a row vector. In doing your work in questions on pen and paper, it's quite likely that vector V, although it's written in I and J and K form there, it may be represented as a column vector. So just be aware of that difference in representation. We have now vector W, and what we're going to do is we're going to Control Symbols Template and we're going to assign that. So it's colon equals. The equals sign won't work. It needs to be colon equals. And then we open up the square bracket, 3, comma, -4, comma 8, and then press enter. So we have our 2 vectors assigned, V and W. Now what we want to do is we want to form U. And so U can be assigned to be 2V minus W. Press enter. And we see there that that's our vector U. It's I, the way to read this is it's I minus 2J plus 2K. So it's performed the vector arithmetic for us. Now, if we want to find a unit vector in that direction, what we do is we press menu, 7 for matrix and vector, and then C for a vector operations, and then 1 or enter for unit vector. Notice that it comes up as unit V. Now that's the last time I'm going to show you how to do that through the menu. In subsequent examples, when needed, and also in vectors part 2, I'll type in UNITV. That also works. So we want the unit vector that's in the direction of U, and we press enter, and there we go. So the unit vector that's in the same direction as vector U, given vector V and W, is in this instance 1/3 I minus 2/3 J plus 2/3 K. Moving right along, we have another short exam style question here, and this is going to allow us to exploit or use the norm command. The norm allows us to find the magnitude of a vector. So what we would do here is we want to use vectors to find the perimeter of a triangle whose vertices are given there. So this is a 3-dimensional situation. And what I've already done is I've already assigned vector OA to be I plus 2J plus 3K. I've assigned vector OB to be 2I plus 3J plus K. And then the remaining vector is the vector, position vector AB, and that's given by OB minus OA. And when that's assigned AB to be vector OB minus vector OA, we get I plus J minus 2K. So we have now the 3 required position vectors. Now what we want to do is we want to work out the magnitude of each of the sides, add them together, and that should give us the perimeter. So to find the norm command, we press menu, 7 for matrix and vector, 7 for norms, and then 1 for norm. And now you've got a choice here. You can either type in OA, or if you press var, what you can do is you can select OA. Okay, so that's going to give us the length of the first side length. Now what I'm going to do is rather than use the menu or the menus, I'm going to type in norm, open bracket, OB. Notice that OA and OB are bold and italicized, and that's because they've been assigned. They've been assigned as a vector. If they just were normal print and italicized, that means we've done something wrong. So that's a good check. Plus norm of AB. And so they're our three side lengths. We add them together to form the perimeter. We press enter and we get the answer correct. 2 decimal places would be 9.93. Just studying those three vectors, the first one has a magnitude of root 14. That one has a magnitude of root 14, and that one has a magnitude of root 6. So we could confirm this by saying, well, let's go 2 times the square root of 14 plus the square root of 6, and that's what it is in exact form. Okay, so just be aware whether you are required to express your answers in exact form or you're allowed to express your answers in floating decimal point form. Moving right along, very important vector quantity is the scalar or the dot product. And so the scalar or dot product of two vectors A and B, which, as the name suggests, when you perform this particular operation, you get a scalar, you get a number. So A dot B is equal to the magnitude of A times the magnitude of B times cos of the angle between the two vectors, and that's the angle that's made between the two tails. So there, those three quantities are all numbers, and hence that gives you a cue as to why A dot B turns out to be a number or a scalar. Similarly, you can work out A dot B in what's called component form, where vector A is A1I plus A2J and A3K, and vector B is B1I plus B2J plus B3K. And this is basically saying that A dot B is the product, is the sum of A1B1 plus A2B2 plus A3B3. The result is a scalar, and from the matrix and vector menu, what you would do is menu, matrix and vector, advanced vector operations, and then number 3 is dot product. And if you wanted to just type it in, it's DOTP. So the next page, this is a nice demonstration of the dot product. So what we have is we have a vector A with a magnitude of 1.2, a vector B with a magnitude of 2.5, and we've got the angle between those two vectors is there. It looks to be about sort of 30, 35 degrees. This here is the dot product, and it is basically the distance on that number line from the origin. So it seems to be about sort of 2.5. And the dot product is the product of the magnitude of vector A, the magnitude of vector B, and the angle between the two vectors. And what we can do is we can show you, if we grab vector B, so we increase the magnitude of B, we can increase the value of the dot product. So that dot product there is about 3. What we can do is, now we're bringing it closer and closer and closer there. Now at the moment, the angle between the two vectors is acute. Get it really close there. Now that seems to suggest that the dot product, when the two vectors are perpendicular to each other or at right angles, given they're non-zero, is 0. So we've just stumbled upon a condition for the dot product of two non-zero perpendicular vectors. Moving it out here, what you'll notice is the dot product, the value becomes negative. So when you have the angle between the two vectors being obtuse, the dot product, or the value of it, is negative. So that's a nice demonstration geometrically of the dot product. The other nice thing you can do is we can have vector A move, vector B, bring that down there so that they're parallel. And what you'll see there, if they're parallel and about the same, they're the angle between the two vectors is 0. So basically the dot product becomes the magnitude of A times the magnitude of B. So let's look at an application of the scalar product, or the dot product. So we've got vector A and vector B are those vectors there. We want to find the dot product and hence find the angle to the nearest minute between A and B. So let's see how we can use Nspire to perform this calculation. Vectors A and B have been assigned as shown there. And so our first task is to find the dot product. So if we press menu, 7 for matrix and vector, and then C for advanced vector operations, and then 3 for dot product. Right, so there's our DOTP. The syntax for this is simply vector A, comma, vector B. Press enter, and that's the value for the dot product. And you can check that by saying, well, okay, 2 times 3 is 6, negative 4 by negative 1 is 4, 1 by negative 4 is negative 4, so 6 plus 4 minus 4 is 6. So, you know, be aware that there'll be questions where you will not be allowed to use your technology, and if you are using the technology, just make sure that you've got a good idea that the answer you've obtained sort of makes sense. Now, the next thing we want to do is our formula is A dot B is the magnitude of A times the magnitude of B times cos theta. So if we divide both sides by the magnitude of A times the magnitude of B, we get cos theta equals A dot B on the magnitude of A times the magnitude of B. So let's insert into Nspire the right-hand side of that formula. So what we're typing out here now is cos theta equals. So we get our fraction template, control divided by. So we go up and grab our dot product. Could have grabbed the 6, that's also fine. Then in the numerator, what we want to do is we want to form the magnitude of A times the magnitude of B. And using the Nspire commands, that is norm. So we want norm of A multiplied by norm of B. Now, I've just typed that in rather than going into the menu. Note that that's what cos theta equals. And also, when you're showing your working, use correct mathematical notation. Don't use machine notation. We press enter, and so cos theta equals that. So now what we want to do is we want to find what theta is. So it's going to become the inverse cos of this. So if we press trig and then find cos to the negative 1 or inverse cos, go up and grab either the input or the output, bring it down to a new entry line, enter, enter. So that's what theta equals in radians. Now the question asks us to find the angle in degrees to the nearest minute. So if we press the catalog button, which is the open book icon, we go to number 1, which is our list of A to Z commands, and fortuitously, it has landed on the convert your angle to degrees, minutes, seconds. So the arrow is the conversion Q, and then DMS is degrees, minutes, seconds. So if we press enter, it says, well, let's take the answer and we're going to change that and convert it into degrees, minutes, seconds. We do that, and to the nearest minute, that's 75 degrees, 7 minutes. Notice that that is an acute angle, and it makes sense because the dot product was a positive value, was greater than 0. Moving right along, perpendicular vectors. 2 non-zero vectors A and B are perpendicular if their scalar product or dot product is 0. There's the situation there. Go to the next page. We can use the scalar product to verify perpendicularity. Easy for you to say. So triangle AOB has those vertices. Verify that triangle OAB is right angled with the angle at the vertex O being 90 degrees. So basically what we want to do is we want to say, well, let's calculate the dot product. So DOTP, notice that it comes up non-italicized, so it recognizes that, the Nspire recognizes that as a command, and then open bracket, and then if you pressed var OA, comma, var stands for, we're short for variable, OB, press enter. The dot product is 0, and so we've verified that triangle OAB is right angled, and the right angle occurs at vertex O. Okay, moving right along. The other type of product in vectors is the cross product or the vector product. So if you have two vectors, A, B, and you form the cross product, what happens is you form a vector which is perpendicular, A cross B is perpendicular to those two vectors. The magnitude of the vector is given by the product of the magnitude of A, the magnitude of B, and sine of the angle theta. In component form, if you've got your two vectors, the vector product is given by that expression there, and the cross product can be found using the cross P command, which is in the same menu as the dot product. Okay, so it'll be matrix and vector, advanced vector operations, and then cross product. Okay, move to the next page. Let's look at an exam style question. Here we're asked to find a unit vector, find a unit vector, and I'll come back to that in a moment, that's perpendicular to each of those vectors A plus B and A minus B, where A and B are those vectors, given vectors. So what I've done here is, again, I've assigned vector A to be that and vector B to be that. Now, you can do all this in one hit, but it's nice to show the working, the progressive working. So let's now form vector A plus B. So if we type in A plus B and press enter, it should make sense there that A plus B is 4i plus 4j plus 0k. And similarly, A minus B is the vector 2i plus 0j plus 4k. Now what we want to do is we want to find let's first of all find a vector which is perpendicular to those two. So we're going to have to use the cross product. So if I actually type in CROSSP, rather than getting it from the menu, that is how you obtain the cross product command. Then open bracket, and then if we type in A plus B, comma, A minus B, and press enter, that gives us a vector which is perpendicular to both those two vectors, mutually perpendicular. Notice, just while we're here, that if I swap these, A minus B, A plus B, we should end up with the negative, and there we go. So I know we haven't got to the unit vector yet, but there are two vectors that are perpendicular to these two vectors, and they're in opposite directions to each other. And you can see that because each component is of an opposite sign. And that's why the question says find a unit vector, because there are two possible answers. And here's one of them. We take unit V, right, unit vector V, go up and grab the first one, for example, press enter, and a unit vector which is perpendicular to those vectors, where A and B are those vectors, is 2/3 I minus 2/3 J minus 1/3 K. Okay. Now let's look briefly at vector equations of lines. Basically, we're defining R of T to be the sum of a position vector OA, or vector A, which is of a point A on the line, and also a vector D, which is parallel to the line. So in other words, vector RT is equal to vector A, which is a position vector, plus a parameter T, a real parameter T, times the direction vector D. A brief exam style question, which can be very easily done without the calculator, but we'll show you how to do it on the calculator, is verify that that point lies on the line represented by that a vector equation. So what we're going to do here is we're going to first of all, now if this question was one of 5 or 6 parts using the vector equation of the line and this point, then it's a very good idea to assign the vectors. This may not be the most time-efficient way to do this question because it's just one part, but we'll show you how to do it anyway. So we want vector OP, and we want to assign that to be -5, 10, 3. Press enter. And then we want to assign the vector equation. Now, I can assign it to be R of t, actually. So R open bracket t, sort of like it's sort of like a function, isn't it? Control symbols template. And then we're going to, and I'm going to combine this now into the I components are 3 plus 2t. The j components are -2 minus 3t. And the k component is 7 plus t. Press enter. And we've received the reply done. So let's just check that that's all right. 3 plus 2t minus 2 minus 3t, 7 plus t. Hopefully you can see where that comes from. Now, what we want to do is we want to take, we want to set, let's say the I components, set them to be equal to each other and solve for t. So if we press menu, it's a simple linear equation which can be solved quite readily by hand using Nspire menu numerical solve, which is okay to use because we have got a linear equation with just one solution. We want to solve 3 plus 2t equals -5 for t, and we get a value of -4. So t equals -4. So to verify that this point lies on the line, what we could do now is we could type in OP. We could set that equal to R of -4, and if press enter, and we get true, true, true. And if you get a row vector that says true, 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 it means that t equals -4 satisfies the j component equation and the k component equation, and so therefore we have verified that that point lies on that line. Moving right along, we want to find the position vector of the point of intersection of those two lines. So I've taken the liberty to assign them. So R1 of t is that, and R2 of s is that. So notice that there's different parameters, t and s both being real. So what we want to do here is we want to take two of the equations, solve them for s and t, and then verify that those values satisfy the third equation. So what we're going to do is we're going to use simultaneous equations. So if we press menu, 3 for algebra, and then 2 for solve systems of equations, we want to solve two equations, and our variables are t, s. Press OK or enter. So we've got our template set up. So our first equation is 2 plus t equals 2 plus 2s. And our second equation, so that's the I components, the j components, -2 minus t equals 4 plus s. They're the j components. And we solve there by pressing enter. And what we get is we get t equals -4 and s equals -2. So to verify this, if we now go R1 of -4, we get the position vector -2i plus 2j plus k. And if I type in R2 of -2, press enter, we get the same vector. So what we've done there is we've verified that the equation, the values for T and S hold in the third equation, and so therefore the position vector of the point of intersection of those lines is actually that there. Moving right along, lines in three-dimensional space. So a pair of lines, they either intersect, so one point of intersection, a unique solution, or they're parallel, the lines do not meet, there's no solutions, or they are coincident, the same line, infinitely many solutions. There is another situation. Lines in three-dimensional space can also be skew lines. Two lines are said to be skew if they do not intersect and are not parallel. So skew lines are on different planes and do not intersect. So a way to visualize skew lines is imagine you're sitting in a room facing a wall, the top horizontal ceiling line in front of you and the bottom floor line on your right-hand side are examples of two skew lines. Here is an exam-style question which I've completed, and I'll just talk you through it. Show that the following two lines, represented by those vector equations, so they're vector equations of a straight line, show that those two lines are indeed skew lines. Okay, so I've assigned R1 of S to be that vector there, and R2 of T to be that vector there. And when you solve those simultaneously, you take the I components, well, I've taken the I components, set them to equal each other, the J components, set them to equal to each other, and then solve for S and T. I get S equals 1 and T equals 0. A point that I would like to make actually is, first of all, notice that they're not parallel. So you've got these two conditions, not parallel and not intersecting. And you look at this direction vector and that direction vector. Now you can't write that as a combination of that vector. So in other words, parallel vectors satisfy the condition vector A equals a scalar K times a vector B. Now if that's true, then they're parallel. But if vector A doesn't equal a scalar K times vector B, then they're not parallel. So we can tell that they're from those directions that they're not parallel. Now we're looking at the condition of not intersecting. So with S equals 1, we get our position vector is I minus J plus 5K, and with T equals 0, we substitute that in and we get I minus J plus 4K. These are different, so therefore they're non-intersecting. So we've shown that they're not parallel, they're not intersecting, and hence they are skewed lines. Finally, we're looking at planes in three-dimensional space, and a plane in three-dimensional space can be expressed in that vector form, the dot product form, or in Cartesian form. I'll bold this when I send this to you, where A is the position vector of a point A on the plane, and vector n is the vector that's normal to the plane, and k is equal to the dot product of an. So you can't do much here, but what we can do is we can use the 3D graphing feature to visualize what a plane looks like. And so here is a situation where we're asked to plot the graph of that plane. So what we're going to do is we're going to press Menu, 2 for View, and then 3 for 3D graphing. We also need to express Z in terms of X and Y. So we've got to transform that equation. So what we do in here, because we see that we want Z in terms of X, Y, so by setting up a fraction, control divided by, we can say that Z is equal to 4 minus X minus 2Y all over 2. Press enter, and there is our plane, and then we can rotate that around like so. There is a menu command, so menu actions, and you can rotate, you can auto rotate, you can change the appearance, etc., etc. So that's worthwhile having a play with. As I said, it's only really just a visualization tool. There's not much you can actually do with it in terms of calculations. Finding the point of intersection of three planes. So the three planes there intersect at the point P. Find the coordinates of P. What I've done here is those three planes, you can set up a system of 3 by 3 equations, 3 equations and 3 unknowns, solve them using the command, and the point of intersection there is x equals 2, y equals -1, z equals 3. As Jim expertly showed yesterday in matrices 1, we can assign matrix A to be the coefficient matrix there. We can assign matrix B to be the column matrix of the coefficients. So hopefully you can see there's enough, you can see where that comes from and where that comes from. And there's a heap of matrix commands that are on offer here to be able to solve this system as well. The first one that I want to show you is if you press menu 7 for matrix and vector, number 6 is simultaneous, the simult command. So if you press A, B, press enter, and there is your solution. Simultaneous is a command that works in mysterious ways. It's just a black box, out comes the answer. Another way to do it, as Jim showed yesterday, was reduced row echelon form. Menu, 7 for matrix and vector, 5 for reduced row echelon form. But what we need to do is we need to combine matrix A and B, and we use a command called the augment command. So we go menu, matrix and vectors, number 1 for create, number 8 for augment. So what we want to do is we want to bring A and B together, A, B, press enter, and that's lovely. The output there is saying that x equals 2, y equals -1, z equals 3. And the other approach is using inverse matrix considerations. You can say that it's A to the power of -1 times B. If you've got a matrix equation AX equals B, then X equals A to the -1 times B using pre-multiplication of the inverse, and you get that result as well. So Nspire is rich in ways in which you can solve systems of equations. That is a visual representation. Those three planes meet at a point. And finally, we've got all these wonderful situations for intersecting planes. The first one is that the planes intersect at a point. There's exactly one solution. The normals are not parallel and not coplanar. So there's case 1. Case 2, the planes intersect in a line. There's an infinite number of solutions. The Jim showed you that yesterday. The normals are coplanar but not parallel. So there's a situation of the planes intersecting in a line there, L. Next, we've got a situation where L is the line of intersection of 2 coincident planes and a third plane not parallel to the coincident planes. We've also got where the 3 planes are coincident. There's an infinite number of solutions. The normals are all parallel. And then we've got these situations for the non-intersecting planes. The first case is that the normals are coplanar but not parallel. So what you do there is you form that triangular prism formed by those three lines. Second situation, the 2 planes are parallel and distinct, and the third plane is not parallel. 2 of the normals are parallel, and the 3 planes are parallel, and at least 2 are distinct. And 2 planes are coincident, and a third plane is parallel and non-coincident with the first 2 planes. So just to finish up, Jim showed a couple of beautiful slides yesterday. So there's the situation of three planes meeting in a line, and that is telling you that you've got an infinite number of solutions because you've got your solutions expressed in terms of a parameter. Jim also showed this lovely slide yesterday. Here we've got the no solution situation, and when you use reduced row echelon form, you get that inconsistent situation, right? And when you use linear linsolve, no solutions are found. Okay, so thanks very much for sticking with me there for 40 minutes or so. So thank you very much for listening. We know it's a tricky time for you with this coronavirus. We hope you got some use out of this webinar. Good luck with your studies, and join us for part 2 vectors soon. Thank you. Bye.